Hey everyone! In this video, we're going to learn how to add vectors. We're going to use displacement vectors, but the same things apply when we add any type of vectors, like velocity, force, or momentum vectors later in the course. In the first example, we'll learn how to add one-dimensional vectors. Then in the second example, we'll add two-dimensional vectors. And the third example will include negative components and how to work with different types of angles. At the end, we'll learn how to add vectors graphically using the tip-to-tail method. For these examples, we're going to follow the displacement of a boat. Let's say the boat moves 50 meters to the right in the x direction, and then it moves 20 meters up in the y direction. During the first part, this is the boat's displacement vector, which we'll call d1 for displacement 1. It has a magnitude of 50 meters. The second displacement vector, d2, has a magnitude of 20 meters. What is the boat's total displacement, specifically the magnitude and direction? The boat traveled these two displacements, but we want to find the vector that tells us the total displacement between the start position and the end position. This vector, d total, is the sum of the d1 vector plus the d2 vector. This is what we call the resultant vector when we add d1 plus d2. So how do we find the magnitude and the angle of d total? We learned in a previous video that if we want to find the magnitude and angle of a vector, we need to know its x and y components. So how can we find the components of d total? First, we need to find the x and y components of d1 and d2. Second, we add the x components to get the total x component, and we add the y components to get the total y component. Third, we use the total x and y components to find the magnitude and angle of the total displacement vector. Let's walk through each step. First, let's find the components of d1 and d2. d1 is pointing directly in the positive x direction, so delta x1, the x component, would be 50 meters, the same as the vector itself. d1 doesn't have a y component because it's parallel to the x-axis, so delta y1 would be 0. d2 is pointing in the y direction, so delta y2, the y component of d2, is 20 meters. d2 doesn't have an x component because it's parallel to the y-axis, so delta x2 is 0. Now, let's find the x and y components of d total. Delta x total would be delta x1 plus delta x2. Delta x1 is 50 meters and delta x2 is 0. So delta x total is just 50 meters. We do the same for the y components. Delta y1 is 0 and delta y2 is 20 meters. So delta y total is 20 meters. This is the simplest example of adding two vectors because each vector is one-dimensional. We might have been able to see that the x component of d total is 50 meters and the y component is 20 meters. But it's worth walking through the steps, and we'll do a more complicated example next. So now that we have the components of the total displacement vector, we can find the magnitude and the angle. Remember, the components and the vector form a right triangle, so we can use geometry and the trig functions to find what we're looking for. For the magnitude, we use the Pythagorean theorem. We're not going to write the total subscript to keep things easier to read. We plug in 50 for delta x and 20 for delta y, and we find that the magnitude is 53.85 meters. For the angle, we use the inverse tangent function. If we want to find this angle, then we plug in 20 for delta y, which is the opposite side, and 50 for delta x, which is the adjacent side. That gives us 21.8 degrees for this angle. So the boat traveled along displacement 1 and displacement 2, and its total displacement was 53.85 meters at an angle of 21.8 degrees. 53.85 meters is the straight line distance between the start point and the end point. So that's how we add one-dimensional vectors to find a total vector, or a resultant vector. Now let's do another example and see how to add two-dimensional vectors. This time, the boat travels 40 meters at an angle of 15 degrees, and then it travels 36 meters at an angle of 56 degrees. What is the boat's total displacement? Like before, the total displacement vector starts at the beginning of the first vector, d1, and ends at the end of the second vector, d2. So it points from the boat's start position to the end position. To find d total, we need to find its x and y components. Again, the total x component will be delta x1 plus delta x2, and the total y component will be delta y1 plus delta y2. Hopefully this makes sense. First, the boat moves to the right a displacement of delta x1. Then it moves to the right again, a displacement of delta x2. So its total displacement to the right is the sum of those two displacements, delta x1 plus delta x2. And the same thing is true for the y direction. The boat moves up delta y1, and then it moves up again delta y2. So overall, it moves up a total of delta y1 plus delta y2. So let's find the components of d1 and d2. Starting with d1. We're going to move quickly through the math, since we've done this a few times, but feel free to pause and check the math if you're not sure about one of the steps. Remember, components form a right triangle with a vector, so we use the right triangle trig functions to find the components. Delta x is adjacent to the 15-degree angle, so delta x equals d times the cosine of theta. We plug in 40 meters for d and 15 degrees for theta, and we get 38.64 meters for delta x. Delta y is opposite from the 15-degree angle, so delta y is d times the sine of theta. Again, we plug in 40 meters for d and 15 degrees for theta, and we get delta y is 10.35 meters. So those are the x and y components of the first vector, d1. Now let's move on to d2. Delta x is d times the cosine of theta. Now we plug in 36 meters for d and 56 degrees for theta. When we do that, we get 20.13 meters for delta x. Delta y is d times the sine of theta. When we plug in the numbers, we get 29.85 meters for delta y. Those are the x and y components of the second vector, d2. Now, we want to find the components of d total. The x component, delta x total, would be delta x1 plus delta x2. That's 38.64 meters plus 20.13 meters. So delta x total is 58.77 meters. The y component would be delta y1 plus delta y2, which is 10.35 meters plus 29.85 meters. So delta y total is 40.20 meters. Now that we have the components of the total displacement vector, we can find its magnitude and angle. Using the Pythagorean theorem for the magnitude, we plug in 40.20 meters for delta y and 58.77 meters for delta x. That gives us 71.20 meters for the magnitude. To find this angle, we use the inverse tangent function, and we plug in 40.20 for the opposite side, delta y, and 58.77 for the adjacent side, delta x. That gives us 34.4 degrees for this angle. So when the boat traveled these two displacements, d1 and d2, the boat's total displacement was 71.20 meters at an angle of 34.4 degrees. Now let's look at one more example that involves negative components. First, the boat travels 55 meters in this direction, and then 50 meters in this direction. What is the magnitude and angle of the total displacement vector? The first vector, d1, has a magnitude of 55 meters, but this time it's at an angle of 15 degrees below the positive x-axis. Using the convention that we learned in a previous video, we would say it has an angle of negative 15 degrees because it's clockwise from the positive x-axis. This positive 15 degrees would be the reference angle. The second vector, d2, has a magnitude of 50 meters and an angle of 112 degrees. The reference angle would be 68 degrees between the vector and the x-axis. So what do the components look like? There's a lot of stuff overlapping each other in this example, so we're not going to look at everything at once, and we should probably keep track of the numbers on the side. This might look confusing, but everything works the same as before. D1 has x and y components, D2 has x and y components, and D total has x and y components. We're still going to add delta x1 plus delta x2 to get delta x total. And we still add delta y1 plus delta y2 to get delta y total. These might look confusing because they're in different directions, but we'll explain that as we work through the example. So first we need to find the components of d1 and d2. Let's start with d1. Now that we're dealing with negative components, there's two ways we can do this, which we talked about in a previous video. The first method is to use the reference angle between the vector and the x-axis, which is positive 15 degrees. The x component is still d times the cosine of this angle, so we plug in 55 meters for d and 15 degrees for theta, and we get 53.13 meters for delta x. Now we need to check if the component is positive or negative. Since it's pointing to the right in the positive x direction, delta x is positive 53.13 meters. The y component is 55 meters times the sine of 15 degrees, which is 14.24 meters. But we can see that the y component is pointing down in the negative y direction. So delta y is actually negative 14.24 meters. The other way we can do this is by using the conventional way of describing angles. We measure a vector's angle relative to the positive x-axis. Counterclockwise angles are positive and clockwise angles are negative. If it helps, you can draw the vector at the origin of the x and y axes to get a better picture of the angle between the vector and the positive x-axis. This vector is 15 degrees clockwise from the positive x-axis, so its angle would be negative 15 degrees. If we plug negative 15 degrees into the sine and cosine functions, then we still get positive 53.13 meters for delta x. But now the sine function gives us negative 14.24 meters for delta y. So if we use this method and plug in the conventional angle, the positive and negative components are taken care of. Let's save these values for later and find the components of the second vector, d2. This vector has an angle of 112 degrees, and the reference angle is 68 degrees. Let's use the 68 degrees first. The x component would be 50 meters times the cosine of 68 degrees, which is 18.73 meters. But the x component is pointing in the negative x direction, so delta x would be negative 18.73 meters. The y component is 50 meters times the sine of 68 degrees, which is 46.36 meters. That stays positive because the y component is pointing in the positive y direction. Now let's try using the conventional angle of 112 degrees counterclockwise from the positive x-axis. If we plug that in, now we get negative 18.73 meters for delta x, and positive 46.36 meters for delta y. So, those are the components of D2. Now we need to find the components of the total displacement vector. Delta x total equals delta x1 plus delta x2. Delta x1 is 53.13 meters, and delta x2 is negative 18.73 meters. That gives us 34.40 meters for delta x total. Notice how we're adding the two components, but delta x2 just happens to be a negative value, so the math is the same as 53.13 minus 18.73. When we add the components graphically, we start with delta x1, and then we add delta x2, which is negative, and points to the left. So the sum of the two components, delta x total, looks like this. The boat moves 53.13 meters to the right, then 18.73 meters to the left. So the overall displacement is 34.4 meters to the right. This is why we needed to keep track of negative components so the directions add together correctly. Drawing the vectors and components can help us see what's going on, but the numbers take care of things for us. We ended up with a positive 34.4 meters for delta x total, which is the correct value and direction. Now let's find the total y component. We plug in negative 14.24 meters for delta y1 and positive 46.36 meters for delta y2, which gives us 32.12 meters for delta y total. In the y direction, the boat moves down 14.24 meters, then up 46.36 meters, so its total displacement is 32.12 meters up in the positive y direction. Now we can find the magnitude and angle of the total displacement vector using the same equations as before. For the magnitude, we plug in 34.40 for delta x and 32.12 for delta y. And we get 47.06 meters for the magnitude. For the angle, we plug in the same values for delta y and delta x, and we get an angle of 43 degrees. So the total displacement of the boat is 47.06 meters at an angle of 43 degrees. Those are some examples of how we add vectors by using components. Now let's talk about adding vectors graphically using the tip-to-tail method. In the examples we did, the vectors were already drawn for us, but most of the time we're going to be given a word problem like this. A boat travels 55 meters at an angle of negative 15 degrees, and then travels 50 meters at an angle of 112 degrees. What is the magnitude and direction of the boat's total displacement? This is the same question as the last example, except we're only given the values, and we have to draw the vectors ourselves. We could answer this question without drawing anything. If we keep track of the values, we can do the same math as before and get the same answer. But let's see how we would draw the vectors based on this information. It usually helps to draw the x and y axes so we can figure out the angle of the vector. The first vector has a magnitude of 55 meters and an angle of negative 15 degrees. So starting at the origin, we draw a vector that's 55 meters long, and negative 15 degrees means the angle is 15 degrees clockwise from the positive x-axis. That's the conventional way to describe angles, but the question also could have said this vector is 15 degrees below the positive x-axis. Obviously, we can't draw an arrow that's 55 meters long, so just draw an arrow that's large enough so we have enough room to label the magnitude, angle, and maybe the components. Let's move this vector over here for now. The second vector has a magnitude of 50 meters and an angle of 112 degrees, so it's 50 meters long and it's 112 degrees counterclockwise from the positive x-axis. If we wanted to use the reference angle, then 180 degrees minus 112 degrees is 68 degrees. So now that we have these two vectors, how do we add them together? We use what's called the tip-to-tail method. The tail of a vector is the starting point, and the tip is the end point, or the tip of the arrow. A vector points from its tail to its tip, and if we imagine the object moving along the displacement vector, the object starts at the tail and ends at the tip. Using the tip-to-tail method, we draw the first vector, then we place the tail of the second vector at the tip of the first vector. So the second vector starts where the first vector ends. Now the sum of the two vectors, the resultant vector, starts at the beginning of vector 1 and ends at the end of vector 2. That is the tip-to-tail method. If the object moves along the total displacement vector, it has the same start and end point as if it traveled along vectors 1 and 2. This works for adding any vectors, like velocity and force vectors. We can add as many vectors as we want, tip to tail, and the resultant vector will point from the start of the first vector to the end of the last vector. These are two-dimensional vectors, but it works the same for one-dimensional vectors, like adding the components in the last example. We started with delta x1, then we placed the tail of delta x2 at the tip of delta x1. The total x component started at the beginning of the first component and ended at the end of the second component. So that's how we add vectors graphically. That's all we're going to cover in this video, so let's do a summary of the main points. We can add vectors together to find the resultant vector by using components. We start by finding the components of the first vector, then we find the components of the second vector, and we repeat that for every vector that we're adding. Next, we add the x components together and the y components together to find the components of the resultant vector. Finally, we use the components of the resultant vector to find its magnitude and angle. If we want to add vectors graphically, we use the tip-to-tail method. We draw the first vector, and then we start the next vector at the tip of the previous vector. Then the resultant vector starts at the beginning of the first vector and ends at the end of the last vector. This works for any type of vectors, and we can add as many as we want. So that's it for this video. Thanks for watching, and I'll see you in the next one.